We're going to pick up where we left off last time in section 3.4, talking about Bronsted-Lowry acidity, a qualitative perspective, not comparing pKa's, but looking at structures. We're going to look at the conjugate base of each acid. Here's the conjugate base. If that is more stable, then the acid is stronger, and that was what we were looking for, is what causes this base to be more stable. There were 4 factors. We've talked about 3 of them. We use this acronym ARIO to help us remember, and this is roughly the order of importance as well. What atom is it bonded to? Greater electronegativity, larger size makes for a more stable anion. Resonance, if that negative charge is delocalized, it'll be more stabilized, more stable. Induction, if we've got electron withdrawing groups, that'll also reduce the electron density and stabilize it. And the 4th one is what we're going to talk about today. Which of the 2 identified protons in the following compound is more acidic? This guy over here or that guy over there? Well, we need to draw the conjugate bases to compare them. So let's do that. How do we draw the conjugate base? Well, Bronsted-Lowry acid is a proton donor. We get to take the proton off, right? So if we take the proton off this guy over here, what's left? We just leave it like that? No. Oops. Can't just leave it like that. The electrons are still there. Right? Because just lost the nucleus. So there's that one. And we need to do the same thing over here. Get rid of that hydrogen. And we're going to have a lone pair and a negative charge. Now, if we run through A, R, I, the ones we've already talked about, they're all the same. It's not going to explain the difference, if there is a difference. Well, what is different about this carbon and that carbon? See anything different? Yeah, double bond on one, triple bond on the other. So we need to look into that and learn a little more about bonding and atomic orbitals. Which, from the name we should have guessed that maybe orbitals had something to do with it. Quick review here. These are the atomic orbitals. You learned about those in Chem 1A. S is spherical, and the p orbitals look like 2 balloons stuck together. An orbital, if you don't remember, is a region of space that can be occupied by electrons. There's a whole bunch of math involved in that, but we don't have time to go into that today. Electrons, though, behave like waves. This is an important concept. They're particles, but they behave like waves too. This is from quantum mechanics and gets into relativity and fun stuff like that. These orbitals have phases. That's why one of these lobes is red and one's blue. What does a phase mean? Well, the orbitals act like waves in a sense too. And a wave goes up and down and up and down. Imagine this is a wave on a lake. And part of the wave is above the surface of the lake and part of it is below. And so these are opposite phases. Waves can interfere constructively or destructively. So if we have 2 waves that are in phase and they come together, they will add and reinforce each other. We call this constructive interference because it makes it bigger. If the waves are out of phase, and here we're using red to be one phase and blue to be another, then when you bring these 2 together, they cancel each other out. We call this destructive interference, and it becomes smaller. So valence bond theory treats a bond as the sharing of electron density between 2 atoms as the result of constructive interference. So here's 2 hydrogen atoms. These are their s orbitals. When they come together and overlap constructively, we get a shape like this. This cross-section is just showing us that when you cut it, it's symmetrical around the bond axis. It's called a sigma bond. But that's what a bond is in valence bond theory. An important idea is that the orbitals in a molecule are not necessarily the same as the orbitals in an atom. And the way we attempt to explain this is we hybridize the atomic orbitals to achieve hybrid orbitals. This is a mathematical procedure of combining the atomic orbitals to get something that explains the behavior of atoms in molecules. The number of hybrid orbitals will always be the same as the number of atomic orbitals that you mixed. You're not going to get more or fewer orbitals. The type of orbital and its shape will vary with the type of atomic orbitals that are combined. Let's look at the simplest case where we're taking an s orbital and combining it with one p orbital. When we do that, we get two sp orbitals. Sp because it's one s and one p. And this is what they look like separately. We usually draw them together because in the molecule, on an atom, this is how they would be aligned. And these small portions would be inside of the other lobe. It's kind of hard to think about, but we like, those guys are small, we're just not going to pay attention to them. So how does this happen? Well, think of it this way. Here you've got your s orbital, and here's your p orbital. Remember, the p orbital has two different phases. And that ends up looking like a face, but these opposite phases, the blue and the red, those are going to interact destructively, and that side of the orbital is going to be smaller. The other side, where these are in phase, sorry, the iPad was slow there. This will get bigger. You can probably see why I'm not a professional artist. This is adding them, and the other possibility is subtracting. Subtracting is the same as adding a negative. So we'll just take this orbital and change its phase and add it to this s orbital. See what we get. So this is the idea. And then we get destructive interference on this side and constructive interference on the other side. These orbitals are both centered on the nucleus. When they interact by adding, we get an orbital, an sp orbital in this arrangement, in this direction with the large lobe on the left. Over here, same orbitals, but now subtracting because the phase has changed, and we get it this way. So that's how we end up with two orbitals that are in opposite directions. And this is what happens in acetylene, simplest molecule with sp hybridization. So this carbon, we've got a bond to hydrogen and a bond to carbon. What's happened here is we've got one s and one of the p orbitals. They're both in the second energy level. They combine and become degenerate, meaning the same energy. So they're equivalent in the same way that these two p orbitals are equivalent. So what we see here on this carbon atom is here's one of the sp hybrid orbitals, and here's the other one. This one is overlapping with the sp hybrid orbital of the other carbon. This sp orbital is overlapping with the s orbital of the hydrogen, and they're both forming sigma bonds. We have two p orbitals, this one in the vertical and this one more in the horizontal, and those will also overlap and form bonds, but those are pi bonds. They're not symmetrical about the nucleus, about the bond axis. And those are the other two bonds in this triple bond. Well, you can have one s and two p orbitals, and when you combine those, again, you get these kind of drumstick shapes where one side is larger because of constructive interference and one is smaller. But because you have three of them now, you're going to get a trigonal planar arrangement of those orbitals. And this is what happens in ethylene. So here we have a carbon with a double bond to another carbon atom, two single bonds to hydrogen. There's 1, 2, 3 groups bonded to the carbon. This is a 2s orbital and two 2p orbitals. Now we're getting 3 degenerate sp2 orbitals. These have this trigonal planar shape, and they overlap with the hydrogens and with the other hybrid orbital, a hybrid orbital from the other carbon. So we had a sigma bond here, and then the unhybridized p orbitals will form pi bonds, and that's where we get this double bond. We can also have sp3, because in that second energy level there's one s and 3 p orbitals. So combining all of these, this is not, the first one wasn't easy to draw. This is much worse, so I'm not even going to try. You still get these drumstick shapes, but now they're going to be oriented into the corners of a tetrahedron, and we get the tetrahedral geometry. 4 equivalent or hybrid orbitals, and they're called sp3. This is what we've got in methane. So we draw methane flat like this, but we know from experiment that it's not flat. It's tetrahedral. And those 4 degenerate orbitals is what gives methane its tetrahedral shape. So let's look at this compound that we're interested in and identify the hybridization state of ideally each carbon, but we're running out of time, so we're just going to look at those carbons that we're interested in because of our question that we're going to try to get back to. So what about this carbon? What's the hybridization on that guy? Yeah, it's sp2, because we have 1, 2, 3 groups. So if you write it on your fingers, sp, there's 2. So there's 3 groups. Then over here, this guy, what's his hybridization? He's got 2 groups, right? sp. So that's sp hybridized. How does this affect acidity, right? Well, the orbitals, these hybrid orbitals are going to have different lengths. Orbitals with more s character are going to be shorter, and so they're going to hold the electrons closer to the nucleus. Look at this guy. Okay, he's half s and half p, and so he's shorter and squattier than sp3, who's looking a lot more like a p orbital, because he's got 3 parts p and 1 part s. And we can see evidence of this in the carbon-hydrogen bond lengths from ethane, ethylene, and acetylene. And we see that the bond length for the sp hybridized orbital carbon, sp hybridized carbon, is shorter than for the sp2 or the sp3. So what we get is a small difference in electronegativity for the carbon atoms depending on their hybridization. An sp hybridized carbon is more electronegative than an sp2, which is more electronegative than an sp3. So now back to our original question, which of these is more stable? This one, we identified that one's sp3 hybridized, this one's sp2. I'm sorry, this one's sp2, that one's sp. Good grief. Yeah, this one, right? Why? Because this carbon is more electronegative than that carbon. It stabilizes the anion. The bond, this orbital, this sp hybrid orbital is shorter. So other factors being equal, this is our summary of this last point, acidity will vary with the hybridization of the atom. The most acidic will be an sp hybridized, and the least will be sp3, and this is confirmed by looking at the actual pKa's for ethane, ethylene, and acetylene. Acetylene is more acidic. Let's identify the more stable anion and explain why it's more stable. Because if you can't just guess 50-50. The first 3 factors, A, R, I, are the same. We're looking at orbitals, right? What's the hybridization here? We've got 3 carbons in the lone pair. The lone pair counts because what was there before this became an anion? Probably a hydrogen. So this is sp3. That carbon is sp3. And what's this guy over here? He's sp. Which one's more acidic? I'm sorry, more stable. This guy. Why? sp orbital, shorter. Electrons closer to the nucleus, more stable.